Good morning, everyone. Welcome back. So we will be starting with our first session. The theme of the first session is artificial intelligence and big data research and application. This session will be chaired by myself, Akshaya, and Irene. And the AV team for this session is Aarti, Anushka, and Malika. So they will be managing the audiovisual stuff of the session. And the faculty chairs for this session is Santosh Anchumali from EMU and Dr. Sunil Sherlekar from SSL. Okay, so let's begin with the session.
In a world made smaller by ease of travel,
Welcome again. We are beginning with the theme of artificial intelligence, which is based on machine learning and deep learning frameworks, which has pervaded every aspect of our lives. Natural language processing, image and pattern recognition, stock markets, customer preferences, etc., are some of the areas where enormous amounts of data, that is big data, is being generated in real time. These are the domains where AI-based techniques combined with big data have already made a huge impact. Emerging areas of research where AI and big data are beginning to make an impact are materials discovery, drug discovery, climate modeling, and medicine or health sector.
Today's theme is divided into two sessions, that is in the morning and afternoon. We would like to inform you that during the talks for both offline and online, we will stream your live video next to your slides. We have already acquired the presentation from you all with the audio and the video embedded. And if you are here in person, please stand up so that the camera will capture you.
This session, showcasing the theme of artificial intelligence and big data research and application, is chaired by Professor Santosh Ansumali and Dr. Sunil Sherlekar. Professor Santosh Ansumali from the Engineering Mechanics Unit of JNCSR works on the research areas of mesoscale simulation methods, reduced description of kinetic equations, numerical algorithms development, and high-performance computing. Dr. Sunil Sherlekar is the co-founder and director at Sanghya Sutra Labs Limited, which is a group company of Reliance Industries Limited.
At the end of the session, we have organized a question and answer session. So we will take all the questions which are pertaining to the session at the end. There is a 10-minute slot which is allotted. And for asking your question, the offline participants can raise your hand or use the mic which is present on the table. So you have to press the mute button and a red light will come on and then you can speak. If you are unable to do that, just raise your hand and our volunteers will come to you with the mic. For the online participants, just type in your questions in the chat box and we will relay the questions. The audiovisual team will relay the questions to the chairs. Thank you.
We'll start with the first speaker of the session, who is Mitul Kumar Ahirwal, who is an assistant professor at Maulana Azad National Institute of Technology, Bhopal, India. His talk will be on the topic parameter tuning of human decision-making model with consideration of human factors through metaheuristic algorithms.
Good morning all. This is Dr. Mitul Kumar Ahirwal, Assistant Professor, Department of Computer Science and Engineering, MNIT Bhopal. Here I am going to present the topic of parameter tuning of human decision making model with consideration of human factor through metaheuristic algorithms. So these are the outline of this particular presentation. First I will brief you about the human decision making process, what are the motivation for this particular research, framework for human decision making model, and how we are going to incorporate different human factors in this model, then model parameter tuning and optimization, and at last conclusion and references. So as we all know that human decision making is a very complex process, and daily humans are taking lots of daily life decision. So sometimes our conscious mind is taking the decision, or sometimes with subconscious mind we are taking the decisions. So here these are the you can say basic steps inside the human decision making process. So here first we need to identify the problem, then we need to search for the different criterias, weighting of criterias, what are the possible alternatives, then we need to evaluate the alternative, and finally we are able to select the best alternative. So that will be our decision. The motivation behind this particular research is that nowadays all things are going to the computerized, or some type of automation is there in the work, and this automation is basically taking the help of prediction or classification algorithms. But what is the main limitation of these algorithms now is that till now human factors are not incorporated in these prediction and classification algorithm, because as we all know, all humans are affected by these human factors, and their decision will also get changed. So now these are some of the human factors which will affect the decision. So like human emotions, time, uncertainty, surrounding environment, cognitive bias, and past experience. So few of these we are going to include in our model. The framework of model basically consists of utility theory and reinforcement learning algorithm. We are taking the help of gambling task to simulate the decision making process. This is an online platform in which we are able to mimic the gambling task. So some initial money is there and 4 desks are there, A, B, C, D. So any one of desks we need to select, and accordingly we can win or lose the amount. So two type of utility theory is there, expected utility theory and prospect utility theory. The main difference between the expected utility theory and prospect utility theory is that in expect utility theory we are not taking any reference, while in the prospect utility theory we are taking the reference point also. Means reference point we can consider a current wealth status of the person who is playing the game. So these are the basic equations of expected utility theory and prospect utility theory. These are the learning algorithms, like delta learning rule we are using, decay reinforcement learning we are using, and choice rules we are using. These are the equations that are used for the development of the model, and here the main is that through these equations we are trying to predict the expectancy value of the next move. And after the model development we can evaluate the model performance on the basis of mean square deviation error. So this is the entire overview of the model. Model consists of the utility theory, learning rules, choice rules, and model evaluation parameters. This is the setup of experiment. Here we have collected the subject data of 75 subjects, apply the utility function, updating the expectancy value with the help of choice rules, taking the output, and finally evaluating the model. Here mainly we have designed the concept of time factor, the concept of modeling of emotions, and ultimately we have incorporated past experience, uncertainty, time factor, and emotion factor in the proposed equation. After this, we have identified these 4 models based on the expected utility theory or on the prospect utility theory with different learning rules, and we are performing the 20, 40, 60 and 80 simulation. These simulations are very much similar to the iteration. So you can see after the 100 simulation, we are having the quite a small MSD value, means our actual data and our estimated data are very close. After this, we have also performed the training and testing of that model. And after this, as we know, our equation is dependent to the different parameters. So if we can change the value of these parameters, our result will also get affected. So to find out the optimum value of these parameters, we are going to use the Metaheuristic algorithm. So two famous algorithm, Jaya and real coded genetic algorithm, we have used. So this is the simple flow of Jaya algorithm. This is the flow of real coded genetic algorithm, and these are the result. So you can see, as per the previous result, our results are improved, as well as we are able to identify the optimal value of alpha, lambda and c. These are the parameters that are used inside the utility value, prospect utility value and the choice dependent rule. So here is the conclusion, that we have developed a human decision making model which also integrates the human factors like past experience, emotion, time, uncertainty, and it is based on the reinforcement learning. And we have identified the best model as the combination of prospect utility theory, decay reinforcement learning and trial dependency. And after that, we have performed the optimization with the help of Jaya and real coded genetic algorithm. These are the few publications that we have gained from this particular research, and these are the references. Thank you.
The next talk of the session is from Maksimenko, Vladimir, Aleksandrovic. It's titled as Extreme Value Theory Inspires Novel Machine Learning Approach for Epileptic Seizures Detection. He's a researcher from Federal State Autonomous Educational Institution
Dear
of Higher
colleagues,
Education.
my talk is
from
entitled
Russia.
Extreme Value Theory Inspires Novel Machine. Dear colleagues, my talk is entitled Extreme Value Theory Inspires Novel Machine Learning Approach for Epileptic Seizure Detection. I am Vladimir Maksimenko. I work at Immanuel Kant Baltic University in Kaliningrad, and this first slide represents a beautiful view of the Kaliningrad's embankment. First of all, I will give you a brief introduction. What is extreme event? These are events that arise suddenly and strongly deviate from the normal behavior. Following this definition, epileptic extreme events are seizures that arise suddenly and unpredictably. Epilepsy diagnostics requires collecting data for a representative number of seizures to define their onset type. This is only possible during the continuous seizure monitoring, which may last over several days. A big part of the analysis is searching for seizures in these recordings, and the medical specialist may spend hours checking the data of a single patient. They definitely need assistance from the automatic systems for seizure detection to reduce the workload and speed up diagnostics. Machine learning methods address this issue in a supervised fashion. Due to the high inter-patient variability, they may exhibit overfitting and lack of generalization. Extreme events theory, in turn, allow addressing this issue using unsupervised machine learning methods, like outlier detection techniques. These methods are already used by Amazon and Google to detect spam and using banking to detect fraud transactions. We propose using them to detect seizures. The good thing about outlier detection methods is that they use a single patient data for training, C4 variables against between subject variability and overfitting. The next question is, which biomarkers of seizures do we see in the brain signals? Which biomarkers will we load to our machine learning algorithm? To answer this question, I will share a slide in which I present the results of our experiment which we performed in rats. We recorded some seizures in rats. They are shown in figure A. You can see that we detect several seizures during 400 seconds. In rats, seizures occur more often than in humans. That's why we were able to detect several episodes. In figure C, there is a time frequency decomposition of seizure. And we see that the red color illustrates the maximal deviation of the signal amplitude from the normal state. We see that it happens at 7 Hz. So we will use this frequency and plot probability density function that describe normal behavior and extreme behavior. We see that for normal behavior, probability density function follow the Weibull distribution, which is similar to normal distribution. In contrast, for epileptic seizures, there is a heavy tail distribution. It's because the extreme events form the heavy tails that spans over high values of signal amplitude. This heavy tail is a biomarker of extreme behavior, which is observed in any systems which can demonstrate such type of activity. In human data, we also recorded several seizures. In figure E demonstrates that we recorded 3 seizures during the 10,000 second fragment. We were lucky to detect a lot of seizures because typically the seizures in humans occur very seldom. Like the animals' data, we see that seizures are characterized by the strong deviation of a signal amplitude from the background activity, from the normal state. At the same time, the figure B demonstrates that the most pronounced deviation is observed at 4 Hz. But in animals, we saw this effect at 7 Hz. Then we use the 7 Hz signal power to plot probability density function like we did in animal studies. Here, a red line in figure A demonstrates the normal behavior, and the red line in figure B demonstrates epileptic behavior. We see that epileptic seizures in humans also form a heavy tail distribution, which indicate the presence of extreme events. In summary, we conclude that epileptic seizures in humans and in animals obey the criteria of extreme value theory. So the seizures are extreme events. So we can use the outlier detection technique to detect seizures in EEG recording of animals and humans. So we loaded EEG signals to our machine learning algorithm for outlier detection. And this slide represents the results. In figure A, we can see multi-channel EEG signals of the patient, in which we recorded 3 seizures. The figure B demonstrates the average signal power at the frequency of 4 Hz. And the outliers correspond to the seizures. We can see 3 outliers located below the seizures. In figure C, we demonstrate the results of our algorithm. First of all, we were able to detect all 3 seizures properly, so these are marked as true positives. At the same time, algorithm detects events which are not seizures, and we mark them as false positives. Considering data of 83 patients that we recorded in clinic, we divided them into 2 groups. First group is marked by the red color, include patients in which we detected all seizures. It's 100% group. The second group, which is marked by blue color, contains patients in which 0 seizures were detection. It's 0% group. We compared this group and present the results in the figure A. We see that 100% group has a heavy tail distribution, manifesting the presence of extreme events, whereas 0% group demonstrate the absence of the heavy tail. That means that seizures in these patients did not obey extreme value theory. The good thing is we can define this in advance. So first we run this algorithm, and if our patient has a heavy tail distribution, we can apply our machine learning methods. Otherwise, we cannot. At this slide, we estimated the time reduction of the doctor's workload in all patients. We compare the time that is required to analyze all data with the time that is required to analyze output of the program. And in all patients, there was a 95% reduction. So I conclude that our algorithm works. It allows to reduce the workload. And second, we combine extreme value theories, which is physical concept, with machine learning, which is mathematical concept, and successfully address important issue of epileptology, the seizure detection. Thank you for your attention.
Thank you for your amazing talk. The next talk of the session is from Chunling Liu. He would be joining us online from China. He's a professor at Hangzhou Normal University, China, and his talk is titled as Decision Making Under Uncertainty, Data, Information, Decision and Value. Professor, if you're online, you can switch on your video. You can raise your hand and we can give you video privileges if you're online. Thank you so much.
Hello, hello. Hello, everyone. I'm Luo Chunling from Hangzhou Normal University, China. Today, my presentation will be about decision-making under uncertainty. In practice, many decision problems are subject to uncertainty. For example, in the hot movie The Wandering Earth 2, the final decision whether to light the engines is a typical decision problem under uncertainty. Before this decision is made, it is uncertain that whether Beijing could successfully restart the internet and save the Earth. Another typical example is investment. The return rate of securities are usually uncertain. Hence, it is very important to know how to make a right and good decision theoretically and practically. A classical theory for decision-making problem under uncertainty is expected utility theory. Under this theory, a utility function is used to describe the preferences of the decision maker, and alternatives are selected based on expected utility. One thing to note is that different decision makers may have different risk preferences. For example, they may be risk-averse, risk-neutral, or risk-seeking. This difference leads to different decisions. To calculate expected utility, we need to know the utility function of the decision maker. This could be obtained by some specifically designed experiments and surveys. However, this task is usually very hard. In addition, expected utility calculation also need probability distribution of uncertain factors. This could usually be estimated based on historical data. However, this task is also very difficult, especially for problems with a large number of uncertain factors. Though we live in the age of big data, in many practical cases, big data contains much information, but it still cannot guarantee complete information. Hence, it is very important to develop decision-making approaches that could help decision-making based on different types of partial information obtained from different sources. One classical approach for decision-making under partial utility information is stochastic dominance. This approach can compare alternatives based on their probability distributions when utility function is not clear. SDLaw considers a set of utility functions, and it guarantees the preferences of dominating alternative over the whole set of utility functions. SD could help select out potential best alternatives, that is, a set of efficient alternatives. Based on different types of utility information, different SD laws have been proposed. However, existing SD laws still need complete probability distribution information. In addition, they are still not efficient enough to reveal clear preferences in practice. Considering these research gaps, we propose almost risk-averse stochastic dominance. This approach can compare alternatives based on degree of absolute risk aversion. Theoretically, the advantage of this approach is that absolute risk aversion measure is directly related to degree of risk aversion, and it is relatively easy to obtain information about it. The definition of our proposed approach is based on probability distribution. That is, as long as the distribution of x and y satisfy the condition in this definition, then we say that x dominates y by ARSD. We prove that if x dominates y, then the expected utility of y is guaranteed to be no smaller than y. That is, x always preferred by all decision makers in the set of utility functions U R star kappa. Based on ARSD, we further propose a decision-making approach based on mean and variance. In particular, this approach could compare alternatives based on bound of risk aversion and mean variance. The law is presented here. It says that as long as the mean and variance of alternative outcomes satisfy this condition, then the dominating solution is always preferred by decision makers whose utility function is in the set U R star kappa. The key contribution of this approach is that it provides insights on how mean variance analysis can be applied to a wide range of problems, regardless whether the quadratic utility or normal distribution assumption are satisfied or not. Next, we show how our approach could be used in financial analysis. We apply our approach to compare the performance of stocks and bonds in China's market. We consider China's two main stock market index, the SSE index and the SZSE index, and three types of government bonds. About 16 years of rate of return data are used. This is the descriptive statistics of return of these assets. We'd like to know which asset is better for decision makers with different degree of risk aversion. Applying our approach, we find the following interesting points. First, no strong dominance exists for short-term investment. This means that if investor wants to do a short-term investment, no upward recommendations can be made between stock index and government bond. Second, stock preferences exist for the long-term investment. That is, for most risk-averse decision makers, if they want to do long-term investment, they should select stocks rather than bonds. Third, risk-averse decision makers should never select one-year bond. In addition, we find that Shenzhen Stock Index is better than Shanghai Stock Index for long investment horizon for most risk-averse decision makers. Based on this work, currently we are studying portfolio optimization with ASSD constraints. This figure shows the cumulative performance of our approaches. It can be seen that our approaches have better performance than existing approaches. Here is my related publications of this presentation. Thanks for your attention. If you have any questions, you are welcome to contact me.
Thank you, Professor, for your talk. The next talk is from Pratik Kumar. He's a PhD student at Indian Institute of Science here in Bangalore. The talk is titled as Beyond Traditional Computing, Enabling Scalable and Energy Efficient AI Application. Pratik Kumar, you can just raise your hand and the camera will capture you.
Just a few short years ago, the idea of artificial intelligence shaping our world in such a profound way would have seemed like science fiction. But today we are at the brink of this exciting new era. It is crucial that we continue to innovate and push the boundaries of unconventional design methodologies to fully realize the potential of AI technology. This is where my research comes in. So hello everyone, I am Pratik Kumar, a doctoral researcher at Indian Institute of Science, Bangalore, India, and my area of expertise lies at the intersection of hardware-friendly machine learning algorithms, high-performance machine learning computational architectures, and emerging memory devices. Today, this short presentation is going to be on beyond traditional computing, enabling a scalable and energy-efficient AI application, where I'll discuss about the exciting potentials of non-conventional computing technologies such as analog for AI to drastically improve the performance and energy efficiency of AI systems and the implemented applications. So today we are at the dawn of AI revolution, where every aspects of our life from social media to healthcare relies on artificial intelligence. These AI tasks rely on complex algorithms that require billions of calculations to be performed every second, which presents a severe challenge for traditional computing hardwares. First, these calculations requires enormous power for execution. On an estimate training, one such machine learning algorithm consumes electricity equivalent to yearly consumption by 3 households and generate carbon emissions similar to what 5 cars would generate in their lifetime. That's nearly 626,000 pounds of CO2. All these to train AI tasks just once. Therefore, if the same trend continues, we would exhaust the current global energy supply just by the year 2025. Second challenge is that the resources required to train these algorithms are massive. If we compare this with human brain that consumes just 25 watts of power, weigh around 3 pounds and has 86 billion processing units, this gives us a sense that there still exists an order of magnitude difference between what nature has to offer us and what we have achieved. Taking inspiration from this nature's masterpiece, one could take a more closer approach like analog. You see, analog technology is not only 1,000 times energy efficient than currently prevalent digital, but also area efficient. However, analog technology has historically struggled to be used in large scale systems due to severe challenges associated with it. My research aimed to overcome these challenges and demonstrate the potential of analog computing for building large scale AI systems. It is also pretty evident from the recent literature present that why analog is one of the promising technology for AI system of the future. But challenges such as designing system from scratch because of non-modular nature of this technology, challenge of programmability and not being able to process scalable have long held this technology. So what is the solution? In brief, I would present you the project that we call Ahirwal, and it stands for Analog Reconfigurable Technology and Bias Scalable Hardware for AI tasks. And in short, this project stands out because it resulted in India's first analog AI accelerator chipset. We started this project back in 2019 and currently it has gone through 8 stages of development. We started by developing a robust mathematical framework which was then used to design analog computational modules for machine learning application. These modules were then used to design computational cores and finally the analog AI accelerator chipset. Let me present to you India's first indigenous analog AI accelerator chipset called Aryabhat. Aryabhat and its technology allows us to overcome many challenges that has grappled the analog design for decades. This technology allows us to build a fully reconfigurable analog AI accelerator, just like digital accelerator, but much smaller in size and highly energy efficient. It also allows the designed analog AI system to be process technology scalable, which means now one can design AI system in one technology node and port the system in another technology node without any architectural changes, which was not possible previously in analog. This technology also introduces the concept of analog standard cells, which one can use similar to digital standard cells, thereby introducing modularity and robustness in analog design. Furthermore, one can use this technology at different power performance specification. Consider the application at the server where training is very time consuming and take even months. And therefore we want to train faster and we are less bothered about power. There we can bias the whole system for high performance, or consider the application at edge devices where battery and energy is limited and one can tolerate a bit delay. The same architecture can be biased in energy efficient mode. In short, it allows us to inherit the power of modularity and programmability from digital world and combine it with the energy and area efficiency of analog world to create a compact, modular, energy efficient accelerator, which was the missing link for the very long time. Utilizing this in-house technology, we made this novel analog AI chip. We then went ahead to build a compiler that could map the existing code from MATLAB and Python to the computations implemented by the Ahirwal technology. This compiler takes input from the users about different runtime specifications and creates a data flow graph of the required neural computation and map it to the Ahirwal chip. After designing a compiler along with the Ahirwal chip, we realized that testing a complete analog AI chip is an Herculean task and has not been done before. We then designed an open source test framework using PyVisa that integrates high precision test equipments, FPGA, and the test chip on a common platform. Results were finally read into the PC. So to summarize, one starts with the algorithm from the open source machine learning framework, then the custom compiler take those inputs along with the user defined specification and convert it into binaries which are mapped into the Ahirwal chip. Once the mapping is done, the AI test framework automates the testing. So we started with the maths, build the framework, build the system, build the compiler, and also build the test framework. All these provides an ecosystem to keep on adding the current technology to make it sustainable in long run. So this slide presents a quick demo of the AI chip under testing and working utilizing the AI test framework where the values of the chips are mapped from the compiler, both of which are presented here. So this research has made a sincere effort toward establishing analog as a viable alternative computing technology for the future. Using this research, one can build an efficient, scalable, large-scale analog AI system for different AI applications in any technology. One of the goals of this research is also to cater the need of present generation of a student, whereby educational institution can use this chip as a hands-on solution to execute complex AI tasks in real time, because alternatives such as GPUs ranges in thousands of dollars and not everyone can afford it. The goal also aligned with India's semiconductor mission to make India self-reliant in indigenous processor technology. This research will require collaboration from different frontiers and across different disciplines to sustain it in a long run. So thank you everyone. I'm looking forward to have a fruitful collaboration across different disciplines.
Thank you, Pratik. The next talk is from Professor Satyasai Jagannath Nanda. He is assistant professor at Malviya National Institute of Technology, Jaipur, India. The talk is titled as Multi-Objective Optimization Algorithms for Seismicity Declustering India. So if you are in person, you could raise your hand. Thank you.
Good day, everyone. Welcome to SCO Young Scientist Conclave. Today, I am going to present the research topic multi-objective optimization algorithms for seismicity declustering. On this particular research topic, my research group at Department of Electronics and Communication Engineering, Malviya National Institute of Technology, Jaipur, have been working for last 10 years. Seismicity declustering is a problem of segregating an earthquake catalog into main shock, which are the main earthquake events, and backgrounds, which are due to the regular earth movements, and the aftershocks, which are caused by a main shock. So the events can be categorized as some events which lead to trigger the main shock are known as foreshocks. And if we effectively able to classify the foreshock aftershocks from the background event, we can know the correlated nature of the earthquakes. The declustering help us in designing models for probabilistic hazard analysis, and we can able to determine the process or estimate the Poisson process and able to tell the declustering phenomenon to achieve independence of the events, which will help us in forecasting the largest earthquakes of the future. To analyze this particular one, we have taken the historic catalog of 32 years for 4 different regions around the world: Himalaya, California, Indonesia, and Japan. We have downloaded these catalogs by setting these parameters on the Northern California Earthquake Data Center. The red dots over here represents the seismic events, and the yellow dots represents the main shock represented in Himalaya and California region. The same spatial distribution of events is represented for Indonesia and Japan catalog. Yellow dots are the main shocks. These main shocks are distributed over the time. You can observe over here in the form of peaks in this catalog. There are many peaks, and each peak represents a significant number of zoom in number of events occurred on the main shock year. Similarly, the temporal distribution in the form of cumulative events is shown over here, and everywhere wherever there is a main shock, there is deviation from the linearity. The declustering problem is formulated over here as an optimization problem with time domain and spatial domain. We try to optimize 2 statistical variables: coefficient of variance and M-Morsita index. The coefficient of variance is a relationship between the seismic events in the time domain. It is represented over here with the delta t, and the coefficient of variance is nearly equal to 1 when the seismic catalog follows the Poissonian distribution. It is greater than 1 when the catalog is have clustered event and it follows a power law distribution. This M-Morsita index is a statistical function representing in the space domain. Here we divide the entire catalog into m number of grids, and in each grid the relationship between the events we use to calculate. The Morsita index represents a Poissonian process when its value approaches towards 1, and if the value is more than 1, it is representing the clustered nature in various quadrants. We have applied a very popular multi-objective optimization algorithm, NSGA2, reported by Professor Kalyan Dev in 2002, which got more than 44,000 times citation in last years, and it has been widely applied in several engineering fields. We have developed a binary version of this NSGA2 algorithm in which the earthquake catalog is taken as input and the output is the declustered seismic catalog. In this particular process, the input seismic catalog comprise of the time, latitude, longitude, magnitude, and depth, and it has n number of events for a specific region. Here we represent each of the parent of in the evolutionary competition. We have taken n number of parents for the analysis, and each parent is representing, 1 represents a aftershock event and 0 represents a background event. So how many events we are taking as background and aftershock? We need to find out the best suitable combination that will optimize the process. Here we apply a logical and or operation to produce new children, and a logical NOT operation is applied for the mutation operation, and all the processes are carried out in the binary domain to produce new children. To determine whether a solution is better or not, we perform non-dominated sorting. Non-dominated solutions are those solutions which are effective in one particular domain but may not be so effective in other domain. The user has the flexibility to select any particular solution from a set of solutions, and here A and D represents compromised solutions, best solutions. The crowding distance, we do not want all solutions to be crowded together and giving us a single values, so we want diversity among them. The diversity is achieved by the crowding distance assignment operator. So between two different Pareto fronts, if the rank is lower, then that is a better solution. Otherwise, if rank is equal, then whose crowding distance is more, that is a better solution. So originally PT number of parents are there and QT number of parents are generated with crossover and mutation. For the next generation, whose Pareto front rank is lower, that is taken for next generation. And if rank are equal, then some of the solutions are rejected based on the crowding distance operator. The simulation we have carried out in MATLAB platform for Himalaya, California, Indonesia, and Japan. These are the Pareto front obtained for the 4 regions with M-Morshita index in the y-axis and coefficient of variance in the x-axis. Among these solutions, one of the solutions which is close to the origin is taken and the analysis is carried out. The aftershock solutions reported over here for Himalaya and California, they are close to the main shock events. Similar is for the Indonesia and Japan catalog, near the main shock events, there are more aftershocks are reported. Backgrounds are uniformly distributed all over the regions, reported over here in gray color dots. Similarly, reported for the Indonesia and Japan in gray color dots. The temporal analysis is represented over here, where the obtained model output with dark black color is following the same nature as that of the total number of events in the brown color. Whereas the declustered events backgrounds are uniformly distributed over here by the gray color, it is showing that uniform distribution. The cumulative plot represents a linear line over here, linear dotted line, gray color, whereas the aftershock or the clustered event that followed the total number of event pattern. The inter-event time and inter-event distance plot reflect the red color points are the aftershocks and blue color points are the backgrounds. So the clusters, both the clusters are overlapping in nature, so it is difficult for segregation. The proposed model is compared with 3 more models, and the coefficient of variance of the aftershock and the background obtained with our proposed model is better compared to the other 3 statistical models. It is reported over here with dark colors. It is observed that the coefficient of variance of the total event is greater than unity, whereas that obtained with the background is nearly approaches towards unity, which justify that the declustering process is very effective. For the space-time model, the aftershock is greater than the total number of events followed by the background model, which reveals that the aftershocks are the main cause of the spatial clustering. Our group has achieved a good number of publications in Elsevier, IEEE transaction and these journals, and reputed international conferences like CEC over past years. Thank you all.
Thank you, sir. Our next speaker is Pitsik Elena Nikolaevna. She's a researcher at Epileptic Center for Artificial
Hello to everyone.
Intelligence and Neurotechnology from Russia, and the talk is titled as Graph Neural Network Performance Depends on Topological Properties of the Data. If you're online, could you please switch on your video? Thank you.
Will you play my video presentation or should I make a talk?
We will be playing your video presentation.
Okay. Hello to everyone. My name is Elena Pitsik. I am a researcher at Baltic Center for Artificial Intelligence and Neurotechnology. My research topic is GNN performance depends on the topological properties of the data. In this research, we used fMRI functional connectivity data to develop a GNN-based classifier of major depressive disorder. Besides, we studied the relationships between topological features of our dataset and architecture of GNN with the best performance in order to gain some insight into the specifics of GNN's ways of processing of graph-like data. As you might know, GNNs belong to the class of the deep learning methods specifically developed for graph-like data processing. GNNs can be used for classification and prediction purposes at node level, edge level, and graph level. In present study, we focus on analyzing the efficiency of the GNN-based algorithm as a function of the topology of the fMRI-based functional Bayes network. Figure A depicts the experimental procedure. We used a dataset consisting of bold time series recorded from 84 subjects, 49 control groups, 35 from MDD group. During the experiment, all participants were instructed to rest as still as possible, with their eyes closed, and let their thoughts float. Each recording lasted approximately 6 minutes. Resting state fMRI was parcellated into 166 areas according to the automated anatomical labeling atlas AAL3. Then, to estimate the connectivity between the regions of interest, we calculated an average bold time series across the voxels in each parcellation and Pearson correlation coefficients for all pairs of the main parcellation activities. Thus, we obtained for each subject a 166 on 166 symmetric connectivity matrix R, an example of which is presented on figure B. Each cell of this connectivity matrix represents the strength of the connections or edge between two parcels. We applied 20 thresholds THRE to the edge weights in range from 0.0 to 0.95 with step 0.05 and binarized the resulting matrix. As a result, we discarded the less important connections based on the THRE value, leaving only the edges with the strongest Pearson coefficient values. An example of a thresholding procedure for a single subject is presented on figure C. In our opinion, the differences between shortest path distributions for two considered classes can help to explain the results of classification. Therefore, for each THRE, we obtain the shortest path distributions for both groups of subjects, which are shown on this slide. Next, we calculated the performance of 10 GNN models, increasing the number of GCN layers from 1 to 10, to check the possible correlation between the depth of the model and the topological features of the dataset. For each THRE, we calculated the value max GCN that equals the parameter n layers for which the F1 score of the corresponding GNN model was the largest. But first, we explored the dependence of shortest path distribution into groups from THRE. With this goal, we applied the t-test for independent samples to the shortest path distributions. Results are shown in figure B, where the white area highlights the maximum values of t-statistic with the corresponding p-value lesser than 0.05, and D marked is the length of the shortest path for which the differences between the groups are the most pronounced. Figure B shows that an increase of the THRE leads to the formation of a larger amount of shortest path of the length more than 2 in the MDD group compared with the control. The maximum value of THR equals to 0.05 correspond to the D marked value of 2, which indicates the deterioration of long path structures in the MDD group. The results of the F1 score for each model THRE pair are shown on figure C. Here, the white line corresponds to the maximum F1 score for each number of layers parameter. First, we can see that max GCN increases with THRE. Second, the shape of the F1 score increase in figure C is qualitatively similar to the shape of the t-statistic increase in figure B, which indicates the possible correlation between D marked and max GCN. To check this, we applied linear regression to show the relationships between the graph's topology and corresponding GNN performance more clearly, which is shown on figure D. Here we can demonstrate the obvious uptrend, evidencing that the optimal depth of the GNN model indeed correlates with the statistical parameter based on the shortest path distribution. Moreover, the estimation of the relationships between two variables with Spearman correlation also shows an increasing trend between max GCN and D mark. On this slide, we also present the ROC curves for 3 different THRE, where black ROC curve is for the model with 1 GCN block and the red curve for the model with the best performance for this particular threshold. We have found that the optimal depth of the GNN depends on the topology of the analyzed graph. The F1 score varies from 80% to 90%, depending on the GNN depth. The F1 score grows, reaching the maximum value at a certain optimal depth. Again, further increase in the depth causes F1 reduction. Our classifier reached an accuracy of 93% when the threshold value equals to 0.15 and there are only 2 layers in the GNN. Such performance is in line with the achievements of the best connectivity-based classifiers for MDD. Thus, thresholding procedure avoids feeding large amounts of data to the GNN and reduces overfitting. Thank you for your attention. If you have any questions, please contact me using my email. Thank you.
Thank you, Elena. Now we'll move on to the question answer session. The in-person participants can raise their hands or can use the table mic. Our volunteer, you can raise your hand and our volunteer Kamakshi will be getting you the mic.
Thank you. I have a question to Maksimenko Vladimir, because his speech was very interesting for us, as that is a kind of inclusive education approach, and that's why I have a question: how your theory and your development can transmit your results in this area of inclusive education, for example, to help people with these epileptic diseases, and where you can implement, how can you implement your results of your research? Thank you.
Professor Maksimenko.
Yes, can you hear me? Hello?
We can hear you.
Okay, thank you for your question. I think that our results can be used because um, the worst thing in epilepsy is that the seizures arise spontaneously, and between seizures, people can live their normal life. That's why it's important to predict seizure, to let's say give people a signal that the seizure is coming, to ask they um, to be in a safe position, and mm, this it demands the development of the system for seizure prediction. We uh, we was working in this direction and also get several results with the help of extreme value theory. The, following the extreme value theory, the extreme event has some predictors, and we can detect these predictors and predict seizure before it actually starts. So that may help people with epilepsy to to be involved in normal life activities like education or other processes.
Thank you, Maksimenko. The next question.
Yeah, here. So my question is for Mr. Pratik Kumar. This is regarding your analog. So have you have you planned to compare your the digital chip with the analog chip based on cost? Will it affect the cost?
So there are a number of things to consider first, just moving to the cost, right? Cost generally depends on the area, and the more you manufacture, the cost goes down. Since it's a research chip that is developed in-house, now estimating that we take into account number of other things, and we have gone like to the market as a startup, and then the product is in like completely selling, then still I am assuming the cost, if you compare area by area, is going to be almost 37 times. We got this data lower than the currently available GPUs in the market, because you can do the same amount of computation in much smaller area. And when you send the CPU, the chip for fabrication, the cost comes per millimeter square. And then adding some research and the market cost, we did an estimate it's going to be around 37 times lower than what is the available GPU. But still, the product is a testing phase, so that's the thing.
Yeah, thank you.
Thank you, Pratik. Questions?
Thank you. I want to ask question from Chungling Lu, who given the presentation on decision making under uncertainty, if she is online available.
Hello, can you hear me?
Yes. Ma'am,
Okay.
I want to know there are other application area where we can apply the expected utility theory, because whatever I have searched, the application are only in the field of economics and finance.
Thank you for the question. Yes, actually expected utility theory is mainly used, it widely used in financial or investment, but it can also be used in other areas like medicine, as long as it is the same problem. Then in theory, we could use the expected utility theory. Yeah.
Okay, thank you.
Thank you, Professor.
Okay. Okay, thank you.
Any other questions?
Yes, and my question will be to Mitul Kumar, and I would like to ask about the human factors. As we know, the human factors, the list of the human factors is so big, and could you tell what about the list of the collection for their human factors? And do you use all the list or only some factors for your program? And
Yes, actually we have designed the experiment in which we are considering only the time factor. Means if same task, we will set a timeline like that game I have used for the data collection. If we are not making any restriction of time, then people will play that game with a free mind. And if we are putting some restriction like you need to complete that game into the 20 minutes only, so results are different. And in the same we have also designed the experiment to capture the emotions also. Means in between the game we are showing some you can say winning type of picture and sometime losing type of picture. So means in between the game they are generating the emotions like sad or happy. So again we are getting the different type of results in the same game. So for both the data we have constructed the model without the human factor and with the human factors, and after that we are comparing the results.
okay, thank you.
Thank you.
Thank you, Dr. Mitul. Any other questions? Any questions from the participants who are attending the conference online? Please raise your hand. Oh,
I'd like to ask the Maksimenko Vladimir Aleksandrovic about the registration, the signal from the epileptic activity for the samples. And could you explain, includes your experiments only experiments on the rats without any drugs, or you can registration the different signals using the rats with some anti-epileptic drugs? And do you collect this information?
Okay, thank you again for the question. No, we did not use drugs because we were interested in the seizures that occurs normally. We have the special type of rats, blood-dry rats. These rats have a genetic predisposition to absence epilepsy, and so all of them have seizures, and they demonstrate many seizures, tens of seizures per hour. So that was not necessary to use drugs. But I know that my colleagues use drugs to induce or to suppress seizures. So that can also be done in their lab, but we did not use drugs.
Okay, thank you. And I think that it will be useful in your experiments to use drugs and to collect the data, because, as we know, on the base of examples for humans, for example, sometimes it's possible to repeat the different epileptic processes for humans who have already used different drugs from the epileptic activity. Thank you.
Yes, I get your point, but there is also a difference between onset mechanisms induced by the drugs and induced by the normal type of thing. Since we were targeting the normal seizures because we were interested in detecting seizures that can occur in real life without any intervention. So we were focusing on the mechanisms that that underlie these type of seizures, because our hypothesis was that there might be different ways of seizure onset with drugs and without drugs. But it should be tested, I think, because the mechanisms, I think they will be different.
Thank you.
Thank you.
Thank you.
Any other questions? Okay. So if there are no more questions, I would like to conclude the first technical session of the conference themed at artificial intelligence and big data research and application.
Join us while we thank all the speakers, both online and offline, who participated and enlightened us about these topics. We'll break for lunch now and we'll get back for the next session at 2 o'clock sharp so that we can get back to our schedule. Lunch is organized at the conference dining hall. You can follow our volunteers. They'll take you to lunch. See you all soon. Thank you.